Arc length. Objectives. By the end of this lesson, you should be able to find the length of an arc given f of x or f of y on a given interval. Let's start by looking at the formula for arc length with respect to x. So y equals f of x needs to be a continuous and differentiable function defined on a closed interval from a to b. Then the length of the curve is given by L equals the integral from a to b of the square root of 1 plus the quantity f prime of x squared. So this formula, just to talk a little bit about what it's derived from, we're going to have some curve defined from a to b. This curve is f of x, and I want to know how long this curve is. Now we know how to find the length of a straight line. So if this straight line went from a to b, we can find the distance between 2 points using the distance formula. So the distance formula is x2 minus x1 squared plus y2 minus y1 squared, where these two coordinate points are x1, y1, x2, y2. So straight lines we know how to do. Curves we don't know how to find their length. But what we're thinking about doing is thinking about this curve as a bunch of tiny, tiny little line segments. And between all of those little tiny straight line segments, we can find the distance, and then we can add up all those distances. So by this point, we should be thinking, well, if we're trying to make the length of these line segments smaller and smaller, we're thinking about the limit process, making these distances go to 0, and then we're going to add up all those distances. So with calculus, we should be thinking integration. So that's where this formula is sort of derived from. It's an integral. We're adding up all of the distances of all of the little line segments that form the entire curve. So that's where the big square root is coming from. That's where the squared notation is coming from. That's where this formula is derived from. And if we're finding arc length with respect to y, well, now we need a function in terms of y, still continuous and differentiable, and it needs to be defined on y values from c to d. And it's going to be the exact same formula. Our y values extend from c to d, and then we have the square root of 1 plus the quantity f prime of y squared dy. Alright, let's go ahead and start with an example. Find the length of the curve y equals 4 radical 2 over 3 x to the 3 halves minus 1 for x values between 0 and 1. So let's go ahead and write out our formula. Our formula extends from x values 0 to 1, so x equals 0 to x equals 1 of the square root of 1, and then we're going to have plus the quantity f prime of x squared dx. So what goes right here is the derivative of this function. So let's go ahead and find y prime off to the side. So the derivative of this, we're going to use the power rule. This looks ugly, it's just a constant. So we're going to bring the 3 halves to the front. So 3 halves, and then we have 4 rad 2 over 3, x to the 1 half, because we're going to reduce the power by 1. And the derivative of a constant is 0. So now these 3's are going to cancel. This 2 will cancel with the 4 to leave us with a 2 on top. So our derivative is 2 radical 2, and then we have x to the 1 half. So this is the integral that we're trying to solve. So we have the integral from 0 to 1 of the square root of 1 plus. Now this is all multiplication here. So this exponent does distribute over multiplication. So 2 squared is 4. Radical 2 squared is 2, and so 2 times 4 is 8. So my coefficient is 8. And then x to the 1 half squared, the 2 and the 1 half multiply together to give me 1. So this is the integral from 0 to 1 of the square root of 1 plus 8x dx. So how we would solve this problem, we're going to do it by hand, is we would need a u-substitution. So u is 1 plus 8x. du is then 8 dx. So 1/8 du is dx. Now this is a definite integral, so we need to change the limits of integration. So we plug the limits of integration into u. So u of 0, if I substitute in 0 here, I will get out 1. And u of 1, so 1 plus 8 times 1 is going to give me 9. So let's write out our new integral. So this is equivalent to 1/8 that comes from this portion over here when I solve for dx. The integral from our limits of integration are now 1 and 9, so now they are u values instead of x values. And then we have radical u. So now we can ignore that this problem ever existed, right? We don't go back to it, we don't plug the u back in, ever. We just solve this problem, du, and substitute in our limits of integration. So this is going to be 1/8. The antiderivative, this is u to the 1/2. So the antiderivative of this is u to the 3/2 times 2/3, and this is evaluated from 1 to 9. So I'm going to go ahead and pull out this 1/12. So the 2 would cancel and go into 8 4 times. So this is 1/12, and I'm going to pull that out, and then I'm going to substitute 9 into u. So 9 to the 3/2 minus 1 to the 3/2. 9 to the 3/2 is the square root of 9, so that's 3. 3 cubed is 27. So this is 27 minus 1 times 1/12. So 1/12 times 26. So now we can just go ahead and reduce this. So we're going to end up with 13/6. So the length of this curve between x values of 0 and 1 is exactly 13/6. Let's go ahead and work on another problem. This one we're going to go ahead and be able to solve the integral with a graphing calculator, but we have to do the setup of the integral by hand. So find the length of the curve y equals natural log of secant x from x equals 0 to x equals pi over 4. So we're going to set up the integral from 0 to pi over 4 of the square root of 1 plus, and then I'm going to need the derivative of this function as a quantity squared. So over here to the side, I'll go ahead and do the derivative of natural log of secant x. So the derivative, y prime, we put the inside of a natural log function in the denominator, so secant x goes on the bottom, and the derivative of secant goes on the top. So the derivative of secant is secant tangent. So what happens is kind of nice, the secants cancel, so my derivative is tangent x. So that is what is about to go right here. So tangent x as a quantity squared. And now we can solve this on our calculator. So to pull up our calculator to make sure we enter everything in correctly, we'll go to Math 9, and our integral goes from 0 to pi over 4. And here we just need to be careful about the way we enter the integrand. So it's the square root of 1 plus, and only tangent x is being squared. So parentheses, tangent x, and only that trig function is being squared. And we want to make sure that is underneath the radical. And now we need to make sure it's with respect to x. So there's our numerical answer. We'll go to the thousandths place. So the length of the curve is 0.881.